In this video, we discuss the geometric representation of the binary pulse amplitude modulation. Basically, we want a way to represent a waveform. In a lot of cases, we can plot those waveforms in graph, but we want to represent them mathematically as well. Here, we're going to introduce an orthogonal base function. Orthogonal base function is a waveform psi t, which has the duration of tb. That's the pulse interval, but with unit energy. In other words, the energy contained in psi t is 1. We're going to write the waveform x yam t, yam equals to 1 or 2, equals to a scalar multiplied by this orthogonal waveform. Pay attention that notation in the textbook is confusing. And SMT here, that's one notation, represent the waveform is a function of time. And this ESM is scalar, not function of time. When we look at these two notations, we have to say if there is a time t followed by ESM or not. If followed by time t, that's a waveform. If just ESM, that's a scalar. I know the notation here is very confusing. I do use the same notation as our in textbook, but I want to point out where the confusion is. So how do we obtain this coefficient, ESM? So we do integral from 0 to tb, and this waveform, yes, EMT, do multiplication, direct multiplication of this base function, and m equals to 1 or 2. Let's look at an example here. Let's look at the, given this waveform, S1t and S2t is defined. How do we represent this waveform using the geometric representation? First of all, we need to define the orthogonal base function. This orthogonal base function and multiply by a scalar, we should obtain the waveform, the pulse, the binary pulse. So in this case, the waveform, the pulses is rectangular. So therefore, we should know that psi t should be rectangular as well, nothing else. And the duration should from 0 to tb. So therefore, from 0 to tb, rectangular. So now we need to design this magnitude. I call it b. How do we know this b, the magnitude of this rectangular in this orthogonal base? This is psi t. We know psi t, the energy in psi t should equals to 1. So what's the energy? The energy we do integral from tb psi t squared d of t that equals to 1. Right? Therefore, we have 0 to tb b squared d of t that equals to b squared tb that should be equals to 1. So therefore, what's b? B is a square root 1 over tb. So now we totally defined the psi t, the orthogonal base. Next, let's look at the coefficient. The coefficient for this waveform SM, so S1 equals to this waveform S1t multiplied by this psi t d of t. So we multiply this waveform and this waveform together, and we do integral, and this is tb, sorry. This magnitude here, that's a, this is 1 over t square root. So therefore, it's really, when we multiply this together, that's another rectangular, right? That's another rectangular. What's the magnitude? The magnitude is a multiplied by square root 1 over TV. What this equals to, we do this, that's A square root TV. The energy in each waveform is A squared TV. This is also equals to EB, energy per bit. So therefore, A multiplied by square root TB, that equals to square root E of B. Okay, so this is a coefficient for waveform S1. What is S2? What is the coefficient for S2? We do the same thing. We do the integral for S2, and because this is a minus here, we only have negative there. So the result is there's a negative there. And what is that? That equals to negative square root EB. So now, what is a geometric representation? Geometric representation is this. Now we obtain the coefficient for S1, and S2. S1 equals square root EB, S2 equals to minus square root EB. Then what is this two waveforms? First waveform equals to S1. That's the coefficient for the first waveform, square root EB multiplied by the orthogonal base function. Waveform S2 equals to the coefficient S2, that's minus square root EB multiplied by the same base function. So this is the geometric representation. So we need orthogonal base function, that's time domain function, with unit energy and with coefficient. So this is geometric representation. This is how we illustrate the geometric representation. This is orthogonal base function, and these are coefficient. We only have one dimension because that's square root EB and minus square root EB. This is S1 and this is S2. Now let's look at another example for the amplitude modulation. So in this case, S1 has this pulse and S2 has this pulse. Still binary pulse amplitude modulation, because you can see the amplitude, this pulse being flipped. Now let's see how do we obtain the geometric representation here. To obtain a geometric representation, we need to find orthogonal waveform. So in this case, the waveform is like this, the rectangular, the positive rectangular and negative rectangular. The orthogonal base function has to have this format because the pulse is eventually is a scaled orthogonal base. So this orthogonal base has to have the similar shape of the pulses. And this scalar can be positive, can be negative. So we do not worry about the magnitude, but we worry about the shape, time shape. The time factor is factorized into the orthogonal base function now, and this factor is a scalar. And later on in the analysis of communication system, we only talk about this scalar. Let's find the magnitude for this orthogonal base. So I call it here, that's B. The original pulses here, you can see this are symmetric. This is a square root EB divided by TB. Again, we do not use particular numbers. We just use notations to make it general. So this is a positive. We can see this is negative. The magnitude for this rectangular and this rectangular are the same, but the sign is reversed. So therefore, the base function here the magnitude here is b, this is minus b. So what's the value of b? We need to find out based on the orthogonal base has unit energy. So we're going to have the energy, we do TB per psi squared T dash equals to 1. And what is this? And this is a half TB, and then the magnitude is b squared dt plus half TB to TB. The magnitude is minus b squared d of t. And this should equals to 1. And we can solve b. b is equals to square root TB. We have square root 1 over TB and minus square root 1 over TB here. Now, what's the coefficient here? We do the same thing. We do the same integral. Yes, 1 equals to TB and S1t multiplied by per psi t dot. And this waveform multiplied by this form together, this is rectangular, and this is another rectangular. You multiply together, that's another rectangular. So when we do the integral, the magnitude rectangular, that's half TB. This because this magnitude multiplied by this magnitude. So therefore, square root EB TB 1 over square root TB, right? And d of t plus, and this half TB and TB, the magnitude multiplied by this magnitude minus EB TB multiplied by minus 1 over TB and d of t. And if we do this two integral, what this equals to, and this is a TB square root EB and half TB and plus, and this is minus, this is minus, right? Become positive. So EB TB and half TB. What this equals to? This is equals to square root EB. So this is S1. This is a coefficient S1. The coefficient S2, we do the same thing. TBS2 per psi t. So we will obtain minus square root EB. Therefore, the geometric representation for these two waveforms is this base function. Here, this is plus square root EB, and this is minus square root EB. This is S1, the coefficient. This is S2, the coefficient.